As we look back, the cars from the first ever Formula One World Championship race in 1950 are hardly recognisable to the ones we see on track today. But why is this? Technological advancements in materials have enabled F1 cars to become lighter, safer and faster than ever before. Polymers have now become an integral part of Formula One, probably more than you think so. From chassis to steering, engine to tyres, the helmet to the clothes the teams wear, F1 would quite literally not exist without polymers. But firstly, what is a polymer? A polymer can be defined as a large molecule or macromolecule made by linking repeating small units known as monomers. The process of bringing together these individual building blocks is known as polymerization. These polymers can be split into two classes, synthetic and natural. Natural polymers occur as a result of a biological process in nature and can be extracted. They are present in the human body and are often water-based. Synthetic polymers are derived from petroleum oil and occur as a result of a process that takes place in a lab by a scientist or an engineer. We'll firstly be looking at the actual race car itself and the specific polymer uses in each component of the car. Here we can clearly see a few examples of the broad range of polymers that are used in the car itself, and we'll be taking a look into each throughout this video. Aside from the engine and gearbox, a modern Formula One car is made almost exclusively from carbon fibre, or carbon fibre reinforced composites. The discovery of using them was a huge breakthrough in the history of developing F1 racing cars. First appearing with the McLaren F1 team in the 1980s, their lightweight and incredibly strong properties, combined with the ability the material brought to build newly shaped components, became key to a successful car, and thus a race win. Carbon fibre has now become so widespread in Formula One that it typically makes up 85% of the standard car. Though carbon fibre is not itself a plastic, in order to have its strength and durability, carbon fibre has to be combined with another material to provide the properties needed for a race car. One example is polyacrylonitrile, which is the most used precursor for carbon fibre due to its superior strength, stability and higher carbon yield. So how is it made? Firstly, we have to make our monomer from propene and ammonia to produce acrylonitrile. After the addition of a catalyst, known as the initiator, all the individual acrylonitrile monomers would join together to form our polymer. This happens as a result of a process called free radical vinyl polymerization. This is a form of polymerization that, as the name suggests, uses free radicals as the initiator and is used for vinyl monomers such as acrylonitrile due to it containing the functional group of a CH double bonded to a CH2. Next, these long polymer chains are combined with other chemicals and spun into fibres which are washed and stretched. In doing this, you can change the properties of the polymer. The fibres are then spread out and heated from 200 to 300 degrees Celsius in the presence of air to oxidize the fibres. This also stabilizes the polymer as the nitrogen atoms are losing their thermodynamically unstable triple bonds and are ring closing with a neighbouring carbon atom. The next step is carbonization, where the fibres are heated from 600 to 1300 degrees Celsius without oxygen. The carbon fibres vibrate and some of the non-carbon bonds break, releasing them and forming tightly bonded carbon crystals. Polymers that are highly resistant to thermal degradation are being used to produce engine and exhaust parts. One such polymer is polyether-ether ketone, known as PEEK. PEEK is a semi-crystalline thermoplastic with excellent mechanical and chemical resistant properties that are retained to high temperatures. It is comprised of repeating units of two ether groups and a ketone group. This polymer is used to manufacture parts to reduce weight and wear. It does not react or dissolve in most organic or aqueous environments, and it is strong enough to be used in many applications in which cast aluminium is commonly found, such as the wheels on the car and some engine parts like pistons. Because it is a polymer, a special lubricant and seal are not needed to keep it from grinding away at metal parts it may contact, as thermoplastics are self-lubricating. F1 tyres are made up of 10% natural rubber and 90% synthetic rubber, such as styrene butadiene rubber, polybutadiene rubber and butyl rubber, though the exact chemical composition is unknown as manufacturers safeguard their tyre formulas. Synthetic rubber is preferable because different monomers can be mixed in various proportions, resulting in a wide range of physical, mechanical and chemical properties. One specific example of a rubber used in the tyres is polybutadiene rubber. It is a synthetic rubber made from the polymerization of the monomer 1,3-butadiene. Because of its double bonds, butadiene can be polymerized into long chains. However, pure polybutadiene is too soft and elastic for most tyres, which need to be harder and more wear resistant. The polymer with cis double bonds causes bends in the chain, preventing the chains aligning, resulting in a much more stronger material. The more cis bonds in the polymer, the more flexible and elastic it becomes, which is ideal for F1 tyres, as a less flexible rubber would crack from the continual flexing of the tyre and the duress that these tyres go through in these F1 races. We'll now be looking at specific polymer uses in the protective equipment used. The safety of not only the drivers but also the mechanics is crucial to the smooth operation of these races. Aramids, which is short for aromatic polyamides, can be used for their aerodynamic fittings in front wing end plates, but are mainly used for their heat-resistant properties, such as in the race suits. The helmets also contain plastic fibres known as Kevlar, with a shock-absorbing layer of polystyrene or polypropylene underneath to cushion the driver's head. Nomex is a meta-aramid material often used in the suits that can resist exposure to a direct flame for 15 seconds. In the case of an accident or fuel spill, a fire suit made of Nomex or any other flame-retardant fibre will give the driver or crew member extra time to get away without suffering severe burns to the covered parts of the body. To protect the driver's legs at the front of the car, the FIA, which is the governing body of F1, imposed a rule that the first inside layer must be made from Kevlar, as it is an extremely strong synthetic fibre which is highly resistant to penetration forces. The strength of Kevlar comes from its unusually regular internal structure. This has implications for the hydrogen bonding which occurs between the electron-dense oxygen atom and the electron-deficient hydrogen. The all-trans configuration, giving long straight chains, means that the hydrogen bonding can occur very regularly to form a very strong lattice, similar to those formed in crystals. A very prominent issue surrounding polymers and plastics has always been their impact on the environment, and F1 has come under pressure to become a more sustainable franchise. In 2019, they launched a plan to be net zero carbon by 2030. Current hybrid power unit is already the most efficient in the world, delivering more power using less fuel than any other road car. The standard fuel used in F1 was unleaded racing fuel, which contained very high levels of hydrocarbon polymers. Extremely high levels of petroleum hydrocarbons strongly inhibit bacterial growth, resulting in poor biodegradation efficiency. However, F1's new generations of cars, introduced in 2022, are running on E10 fuel, a blend of 90% fuel and 10% renewable ethanol. The construction of the ethanol molecule means it carries a lower quantity of joules per kilogram as a combustible vapour than the equivalent volume of Formula 1 race gasoline. But from 2026, it will get even better, as they will now run on 100% sustainable fuels. Advanced sustainable fuels are made up of components derived from an approved carbon capture scheme. The carbon cycle would be completely neutral, so the carbon utilised to produce that fuel is the same quantity as the carbon emitted from the internal combustion engine. It means that the engines do not add anything to the carbon dioxide in the atmosphere. So, overall, polymers will continue to play a huge role in almost every aspect, but the newest and most exciting area of sustainability and the heightening popularity of Formula E will most likely be the direction for improvement in the future. Thank you.